Scale-invariant feature transform is an algorithm in computer vision to detect and describe local features in images. The algorithm was published by David Lowe in 1999. Applications include object recognition, robotic mapping and navigation, image stitching, 3D modeling, gesture recognition, video tracking, individual identification of wildlife and match moving. The algorithm is patented in the US. The owner is the University of British Columbia. Overview: for any object in an image, interesting points on the object can be extracted to provide a feature description of the object. This description, extracted from a training image, can then be used to identify the object when attempting to locate the object in a test image containing many other objects. To perform reliable recognition, it is important that the features extracted from the training image be detectable even under changes in image scale, noise and illumination. Such points usually lie on high contrast regions of the image, such as object edges. Another important characteristic of these features is that the relative positions between them in the original scene shouldn't change from one image to another. For example, if only the four corners of a door were used as features, they would work regardless of the door's position. But if points in the frame were also used, the recognition would fail if the door is opened or closed. Similarly, features located in articulated or flexible objects would typically not work if any change in their internal geometry happens between two images in the set being processed. However, in practice SIFT detects and uses a much larger number of features from the images, which reduces the contribution of the errors caused by these local variations in the average error of all feature matching errors. SIFT can robustly identify objects even among clutter and under partial occlusion, because the SIFT feature descriptor is invariant to uniform scaling, orientation, and partially invariant to affine distortion and illumination changes. This section summarizes Lowe's object recognition method and mentions a few competing techniques available for object recognition under clutter and partial occlusion. SIFT K-points of objects are first extracted from a set of reference images and stored in a database. An object is recognized in a new image by individually comparing each feature from the new image to this database and finding candidate matching features based on Euclidean distance of their feature vectors. From the full set of matches, subsets of K-points that agree on the object and its location, scale, and orientation in the new image are identified to filter out good matches. The determination of consistent clusters is performed rapidly by using an efficient hash table implementation of the generalized Huff transform. Each cluster of three or more features that agree on an object and its pose is then subject to further detailed model verification and subsequently outliers are discarded. Finally, the probability that a particular set of features indicates the presence of an object is computed, given the accuracy of fit and number of probable false matches. Object matches that pass all these tests can be identified as correct with high confidence. Key stages: scale-invariant feature detection. Lowe's method for image feature generation transforms an image into a large collection of feature vectors, each of which is invariant to image translation, scaling, and rotation, partially invariant to illumination changes and robust to local geometric distortion. These features share similar properties with neurons in inferior temporal cortex that are used for object recognition in primate vision. Key locations are defined as maxima and minima of the result of difference of Gaussian's function applied in scale space to a series of smoothed and resampled images. Low contrast candidate points and edge response points along an edge are discarded. Dominant orientations are assigned to localized K-points. These steps ensure that the K-points are more stable for matching and recognition. SIFT descriptors robust to local affine distortion are then obtained by considering pixels around a radius of the key location, blurring and resampling of local image orientation planes. Feature matching and indexing. Indexing consists of storing SIFT keys and identifying matching keys from the new image. Lowe used a modification of the KD tree algorithm called the best bin first search method that can identify the nearest neighbors with high probability using only a limited amount of computation. The BBF algorithm uses a modified search ordering for the KD tree algorithm so that bins in feature space are searched in the order of their closest distance from the query location. This search order requires the use of a heap-based priority queue for efficient determination of the search order. The best candidate match for each k-point is found by identifying its nearest neighbor in the database of k-points from training images. The nearest neighbors are defined as the k-points with minimum Euclidean distance from the given descriptor vector. The probability that a match is correct can be determined by taking the ratio of distance from the closest neighbor to the distance of the second closest. Lowe rejected all matches in which the distance ratio is greater than 0.8, which eliminates 90% of the false matches while discarding less than 5% of the correct matches. To further improve the efficiency of the best bin first algorithm, search was cut off after checking the first 200 nearest neighbor candidates. For a database of 100,000 k-points, this provides a speed-up over exact nearest neighbor search by about 2 orders of magnitude, yet results in less than a 5% loss in the number of correct matches. Cluster identification by half-transform voting. Half-transform is used to cluster reliable model hypotheses to search for keys that agree upon a particular model pose. Half-transform identifies clusters of features with a consistent interpretation by using each feature to vote for all object poses that are consistent with the feature. When clusters of features are found to vote for the same pose of an object, the probability of the interpretation being correct is much higher than for any single feature. An entry in a hash table is created predicting the model location, orientation, and scale from the match hypothesis. The hash table is searched to identify all clusters of at least 3 entries in a bin, and the bins are sorted into decreasing order of size. Each of the SIFT k-points specifies 2D location, scale, and orientation, and each matched k-point in the database has a record of its parameters relative to the training image in which it was found. The similarity transform implied by these 4 parameters is only an approximation to the full 6 degree of freedom pose space for a 3D object and also does not account for any non-rigid deformations. Therefore, Lowe used broad bin sizes of 30 degrees for orientation, a factor of 2 for scale, and 0.25 times the maximum projected training image dimension for location. The SIFT key samples generated at the larger scale are given twice the weight of those at the smaller scale. This means that the larger scale is in effect able to filter the most likely neighbors for checking at the smaller scale. This also improves recognition performance by giving more weight to the least noisy scale. To avoid the problem of boundary effects in bin assignment, each k-point match votes for the 2 closest bins in each dimension, giving a total of 16 entries for each hypothesis and further broadening the pose range. Model verification by linear least squares. Each identified cluster is then subject to a verification procedure in which a linear least squares solution is performed for the parameters of the affine transformation relating the model to the image. The affine transformation of a model point, xy, t to an image point, uv, t can be written as below. Where the model translation is, txtyt and the affine rotation, scale, and stretch are represented by the parameters m1, m2, m3 and m4. To solve for the transformation parameters, the equation above can be rewritten to gather the unknowns into a column vector. This equation shows a single match, but any number of further matches can be added, with each match contributing 2 more rows to the first and last matrix. At least 3 matches are needed to provide a solution. We can write this linear system as where A is a known m by n matrix, X is an unknown n-dimensional parameter vector, and B is a known m-dimensional measurement vector. Therefore the minimizing vector is a solution of the normal equation. The solution of the system of linear equations is given in terms of the matrix, called the pseudo-inverse of A, by which minimizes the sum of the squares of the distances from the projected model locations to the corresponding image locations. Outlier detection. Outliers can now be removed by checking for agreement between each image feature and the model, given the parameter solution. Given the linear least squares solution, each match is required to agree within half the error range that was used for the parameters in the half-transform bins. As outliers are discarded, the linear least squares solution is resolved with the remaining points, and the process iterated. If fewer than 3 points remain after discarding outliers, then the match is rejected. In addition, a top-down matching phase is used to add any further matches that agree with the projected model position, which may have been missed from the Hough transform bin due to the similarity transform approximation or other errors. The final decision to accept or reject a model hypothesis is based on a detailed probabilistic model. This method first computes the expected number of false matches to the model pose, given the projected size of the model, the number of features within the region, and the accuracy of the fit. A Bayesian probability analysis then gives the probability that the object is present based on the actual number of matching features found. A model is accepted if the final probability for a correct interpretation is greater than 0.98. Low SIFT-based object recognition gives excellent results except under wide illumination variations and under non-rigid transformations. Competing methods for scale-invariant object recognition under clutter/partial occlusion, RIFT is a rotation-invariant generalization of SIFT. The RIFT descriptor is constructed using circular normalized patches divided into concentric rings of equal width, and within each ring a gradient orientation histogram is computed. To maintain rotation invariance, the orientation is measured at each point relative to the direction pointing outward from the center. GRIF, generalized robust invariant feature, is a general context descriptor which encodes edge orientation, edge density and hue information in a unified form, combining perceptual information with spatial encoding. The object recognition scheme uses neighboring context-based voting to estimate object models. SIRF, speeded up robust features, is a high-performance scale and rotation invariant interest point detector/descriptor claimed to approximate or even outperform previously proposed schemes with respect to repeatability, distinctiveness, and robustness. SIRF relies on integral images for image convolutions to reduce computation time, builds on the strengths of the leading existing detectors and descriptors. It describes a distribution of Haar wavelet responses within the interest point neighborhood. Integral images are used for speed and only 64 dimensions are used, reducing the time for feature computation and matching. The indexing step is based on the sign of the Laplacian, which increases the matching speed and the robustness of the descriptor. PCA SIFT and GLOH are variants of SIFT. PCA SIFT descriptor is a vector of image gradients in x and y direction computed within the support region. The gradient region is sampled at 39x39 locations, therefore the vector is of dimension 3042. The dimension is reduced to 36 with PCA. Gradient location orientation histogram is an extension of the SIFT descriptor designed to increase its robustness and distinctiveness. The SIFT descriptor is computed for a log polar location grid with 3 bins in radial direction and 8 in angular direction, which results in 17 location bins. The central bin is not divided in angular directions. The gradient orientations are quantized in 16 bins, resulting in 272 bin histogram. The size of this descriptor is reduced with PCA. The covariance matrix for PCA is estimated on image patches collected from various images. The 128 largest eigenvectors are used for description. Wagner et al. Developed 2 object recognition algorithms especially designed with the limitations of current mobile phones in mind. In contrast to the classic SIFT approach, Wagner et al. Used the fast corner detector for feature detection. The algorithm also distinguishes between the offline preparation phase where features are created at different scale levels and the online phase where features are only created at the current fixed scale level of the phone's camera image. In addition, features are created from a fixed patch size of 15x15 pixels and form a SIFT descriptor with only 36 dimensions. The approach has been further extended by integrating a scalable vocabulary tree in the recognition pipeline. This allows the efficient recognition of a larger number of objects on mobile phones. The approach is mainly restricted by the amount of available RAM. Features: the detection and description of local image features can help in object recognition. The SIFT features are local and based on the appearance of the object at particular interest points, and are invariant to image scale and rotation. They are also robust to changes in illumination, noise, and minor changes in viewpoint. In addition to these properties, they are highly distinctive, relatively easy to extract and allow for correct object identification with low probability of mismatch. They are relatively easy to match against a database of local features, but however the high dimensionality can be an issue, and generally probabilistic algorithms such as KD trees with best bin first search are used. Object description by set of SIFT features is also robust to partial occlusion. As few as 3 SIFT features from an object are enough to compute its location and pose. Recognition can be performed in close to real time, at least for small databases and on modern computer hardware. Algorithm, scale space extrema detection. This is the stage where the interest points, which are called K-points in the SIFT framework, are detected. For this, the image is convolved with Gaussian filters at different scales, and then the difference of successive Gaussian blurred images are taken. K-points are then taken as maxima-minima of the difference of Gaussians that occur at multiple scales. Specifically, a dog image is given by, where is the convolution of the original image with a Gaussian blur at scale, that is. Hence a dog image between scales and is just the difference of the Gaussian blurred images at scales and. For scale space extrema detection in the SIFT algorithm, the image is first convolved with Gaussian blurs at different scales. The convolved images are grouped by octave, and the value of is selected so that we obtain a fixed number of convolved images per octave. Then the difference of Gaussian images are taken from adjacent Gaussian blurred images per octave. Once dog images have been obtained, K-points are identified as local minima-maxima of the dog images across scales. This is done by comparing each pixel in the dog images to its 8 neighbors at the same scale and 9 corresponding neighboring pixels in each of the neighboring scales. If the pixel value is the maximum or minimum among all compared pixels, it is selected as a candidate K-point. This K-point detection step is a variation of one of the blob detection methods developed by Lindbergh by detecting scale space extrema of the scale normalized Laplacian, that is detecting points that are local extrema with respect to both space and scale, in the discrete case by comparisons with the nearest 26 neighbors in a discretized scale space volume. The difference of Gaussians operator can be seen as an approximation to the Laplacian, with the implicit normalization in the pyramid also constituting a discrete approximation of the scale normalized Laplacian. Another real-time implementation of scale space extrema of the Laplacian operator has been presented by Lindbergh and Breese based on a hybrid pyramid representation. K-point localization. Scale space extrema detection produces too many K-point candidates, some of which are unstable. The next step in the algorithm is to perform a detailed fit of the nearby data for accurate location, scale, and ratio of principal curvatures. This information allows points to be rejected that have low contrast or are poorly localized along an edge. Interpolation of nearby data for accurate position. First, for each candidate K-point, interpolation of nearby data is used to accurately determine its position. The initial approach was to just locate each K-point at the location and scale of the candidate K-point. The new approach calculates the interpolated location of the extremum, which substantially improves matching and stability. The interpolation is done using the quadratic Taylor expansion of the difference of Gaussian scale space function, with the candidate K-point as the origin. This Taylor expansion is given by where d and its derivatives are evaluated at the candidate K-point and is the offset from this point. The location of the extremum is determined by taking the derivative of this function with respect to and setting it to 0. If the offset is larger than in any dimension, then that's an indication that the extremum lies closer to another candidate K-point. In this case, the candidate K-point is changed and the interpolation performed instead about that point. Otherwise the offset is added to its candidate K-point to get the interpolated estimate for the location of the extremum. A similar subpixel determination of the locations of scale space extrema is performed in the real-time implementation based on hybrid pyramids developed by Lindbergh and his co-workers. Discarding low-contrast K-points. To discard the K-points with low contrast, the value of the second-order Taylor expansion is computed at the offset. If this value is less than, the candidate k-point is discarded. Otherwise it is kept, with final scale space location, where is the original location of the k-point. Eliminating edge responses, the dog function will have strong responses along edges, even if the candidate k-point is not robust to small amounts of noise. Therefore, in order to increase stability, we need to eliminate the k-points that have poorly determined locations but have high edge responses. For poorly defined peaks in the dog function, the principal curvature across the edge will be much larger than the principal curvature along it. Finding these principal curvatures amounts to solving for the eigenvalues of the second-order Hessian matrix, H. The eigenvalues of H are proportional to the principal curvatures of D. It turns out that the ratio of the two eigenvalues, say is the larger one, and the smaller one, with ratio, is sufficient for SIFT's purposes. The trace of H, that is, gives us the sum of the two eigenvalues, while its determinant, that is, yields the product. The ratio can be shown to be equal to, which depends only on the ratio of the eigenvalues rather than their individual values. R is minimum when the eigenvalues are equal to each other. Therefore the higher the absolute difference between the two eigenvalues, which is equivalent to a higher absolute difference between the two principal curvatures of D, the higher the value of R. It follows that, for some threshold eigenvalue ratio, if R for a candidate k-point is larger than, that k-point is poorly localized and hence rejected. The new approach uses this processing step for suppressing responses at edges is a transfer of a corresponding approach in the Harris operator for corner detection. The difference is that the measure for thresholding is computed from the Hessian matrix instead of a second moment matrix. Orientation assignment. In this step, each k-point is assigned one or more orientations based on local image gradient directions. This is the key step in achieving invariance to rotation, as the k-point descriptor can be represented relative to this orientation and therefore achieve invariance to image rotation. First, the Gaussian smoothed image at the k-point scale is taken so that all computations are performed in a scale-invariant manner. For an image sample at scale, the gradient magnitude and orientation are pre-computed using pixel differences. The magnitude and direction calculations for the gradient are done for every pixel in a neighboring region around the k-point in the Gaussian blurred image L. An orientation histogram with 36 bins is formed, with each bin covering 10 degrees. Each sample in the neighboring window added to a histogram bin is weighted by its gradient magnitude and by a Gaussian weighted circular window with a that is 1.5 times that of the scale of the k-point. The peaks in this histogram correspond to dominant orientations. Once the histogram is filled, the orientations corresponding to the highest peak and local peaks that are within 80% of the highest peaks are assigned to the k-point. In the case of multiple orientations being assigned, an additional k-point is created having the same location and scale as the original k-point for each additional orientation. K-point descriptor. Previous steps found k-point locations at particular scales and assigned orientations to them. This ensured invariance to image location, scale and rotation. Now we want to compute a descriptor vector for each k-point such that the descriptor is highly distinctive and partially invariant to the remaining variations such as illumination, 3D viewpoint, etc. This step is performed on the image closest in scale to the k-point scale. First, a set of orientation histograms is created on 4x4 pixel neighborhoods with 8 bins each. These histograms are computed from magnitude and orientation values of samples in a 16x16 region around the k-point such that each histogram contains samples from a 4x4 subregion of the original neighborhood region. The magnitudes are further weighted by a Gaussian function with equal to 1/2 the width of the descriptor window. The descriptor then becomes a vector of all the values of these histograms. Since there are 4x4 equals 16 histograms each with 8 bins, the vector has 128 elements. This vector is then normalized to unit length in order to enhance invariance to affine changes in illumination. To reduce the effects of nonlinear illumination, a threshold of 0.2 is applied and the vector is again normalized. Although the dimension of the descriptor, that is 128, seems high, descriptors with lower dimension than this don't perform as well across the range of matching tasks, and the computational cost remains low due to the approximate BBF method used for finding the nearest neighbor. Longer descriptors continue to do better but not by much, and there is an additional danger of increased sensitivity to distortion and occlusion. It is also shown that feature matching accuracy is above 50% for viewpoint changes of up to 50 degrees. Therefore SIFT descriptors are invariant to minor affine changes. To test the distinctiveness of the SIFT descriptors, matching accuracy is also measured against varying number of k-points in the testing database, and it is shown that matching accuracy decreases only very slightly for very large database sizes, thus indicating that SIFT features are highly distinctive. Theoretical explanation: the SIFT descriptor is based on image measurements in terms of receptive fields over which local scale-invariant reference frames are established by local scale selection. A general theoretical explanation about this is given in the Scale-RPDL article on SIFT. Comparison of SIFT features with other local features: there has been an extensive study done on the performance evaluation of different local descriptors, including SIFT, using a range of detectors. The main results are summarized below. SIFT and SIFT-like GLOH features exhibit the highest matching accuracies for an affine transformation of 50 degrees. After this transformation limit, results start to become unreliable. Distinctiveness of descriptors is measured by summing the eigenvalues of the descriptors, obtained by the principal components analysis of the descriptors normalized by their variance. This corresponds to the amount of variance captured by different descriptors, therefore, to their distinctiveness. PCA SIFT, GLOH and SIFT features give the highest values. SIFT-based descriptors outperform other contemporary local descriptors on both textured and structured scenes, with the difference in performance larger on the textured scene. For scale changes in the range 2-2.5 and image rotations in the range 30 to 45 degrees, SIFT and SIFT-based descriptors again outperform other contemporary local descriptors with both textured and structured scene content. Introduction of blur effects or local descriptors, especially those based on edges, like shape context, because edges disappear in the case of a strong blur. But GLOH, PCA SIFT and SIFT still performed better than the others. This is also true for evaluation in the case of illumination changes. The evaluations carried out suggests strongly that SIFT-based descriptors, which are region-based, are the most robust and distinctive, and are therefore best suited for feature matching. However, most recent feature descriptors such as SURF have not been evaluated in this study. SURF has later been shown to have similar performance to SIFT, while at the same time being much faster. Another study concludes that when speed is not critical, SIFT outperforms SURF. Recently, a slight variation of the descriptor employing an irregular histogram grid has been proposed that significantly improves its performance. Instead of using a 4x4 grid of histogram bins, all bins extend to the center of the feature. This improves the descriptor's robustness to scale changes. The SIFT rank descriptor was shown to improve the performance of the standard SIFT descriptor for affine feature matching. A SIFT rank descriptor is generated from a standard SIFT descriptor, by setting each histogram bin to its rank in a sorted array of bins. The Euclidean distance between SIFT rank descriptors is invariant to arbitrary monotonic changes in histogram bin values, and is related to Spearman's rank correlation coefficient. Applications: object recognition using SIFT features, given SIFT's ability to find distinctive k-points that are invariant to location, scale and rotation, and robust to affine transformations and changes in illumination, they are usable for object recognition. The steps are given below. First, SIFT features are obtained from the input image using the algorithm described above. These features are matched to the SIFT feature database obtained from the training images. This feature matching is done through a Euclidean distance-based nearest neighbor approach. To increase robustness, matches are rejected for those k-points for which the ratio of the nearest neighbor distance to the second nearest neighbor distance is greater than 0.8. This discards many of the false matches arising from background clutter. Finally, To avoid the expensive search required for finding the Euclidean distance-based nearest neighbor, an approximate algorithm called the best bin first algorithm is used. This is a fast method for returning the nearest neighbor with high probability, and can give speed up by factor of 1000 while finding nearest neighbor 95% of the time. Although the distance ratio test described above discards many of the false matches arising from background clutter, we still have matches that belong to different objects. Therefore, to increase robustness to object identification, we want to cluster those features that belong to the same object and reject the matches that are left out in the clustering process. This is done using the Hough transform. This will identify clusters of features that vote for the same object pose. When clusters of features are found to vote for the same pose of an object, the probability of the interpretation being correct is much higher than for any single feature. Each k-point votes for the set of object poses that are consistent with the k-point's location, scale, and orientation. Bins that accumulate at least 3 votes are identified as candidate object pose matches. For each candidate cluster, a least squares solution for the best estimated affine projection parameters relating the training image to the input image is obtained. If the projection of a k-point through these parameters lies within half the error range that was used for the parameters in the Hough transform bins, the k-point match is kept. If fewer than 3 points remain after discarding outliers for a bin, then the object match is rejected. The least squares fitting is repeated until no more rejections take place. This works better for planar surface recognition than 3D object recognition since the affine model is no longer accurate for 3D objects. In this journal, authors proposed a new approach to use SIFT descriptors for multiple object detection purposes. The proposed multiple object detection approach is tested on aerial and satellite images. SIFT features can essentially be applied to any task that requires identification of matching locations between images. Work has been done on applications such as recognition of particular object categories in 2D images, 3D reconstruction, motion tracking and segmentation, robot localization, image panorama stitching and epipolar calibration. Some of these are discussed in more detail below. Robot localization and mapping. In this application, a trinocular stereo system is used to determine 3D estimates for k-point locations. K-points are used only when they appear in all 3 images with consistent disparities, resulting in very few outliers. As the robot moves, it localizes itself using feature matches to the existing 3D map, and then incrementally adds features to the map while updating their 3D positions using a Kalman filter. This provides a robust and accurate solution to the problem of robot localization in unknown environments. Panorama stitching. SIFT feature matching can be used in image stitching for fully automated panorama reconstruction from non-panoramic images. The SIFT features extracted from the input images are matched against each other to find k-nearest neighbors for each feature. These correspondences are then used to find m-candidate matching images for each image. Homographies between pairs of images are then computed using Ransack, and a probabilistic model is used for verification. Because there is no restriction on the input images, graph search is applied to find connected components of image matches such that each connected component will correspond to a panorama. Finally, for each connected component, bundle adjustment is performed to solve for joint camera parameters, and the panorama is rendered using multi-band blending. Because of the SIFT-inspired object recognition approach to panorama stitching, the resulting system is insensitive to the ordering, orientation, scale and illumination of the images. The input images can contain multiple panoramas and noise images, and panoramic sequences are recognized and rendered as output. 3D scene modeling, recognition and tracking. This application uses SIFT features for 3D object recognition and 3D modeling in context of augmented reality, in which synthetic objects with accurate pose are superimposed on real images. SIFT matching is done for a number of 2D images of a scene or object taken from different angles. This is used with bundle adjustment to build a sparse 3D model of the viewed scene and to simultaneously recover camera poses and calibration parameters. Then the position, orientation and size of the virtual object are defined relative to the coordinate frame of the recovered model. For online match moving, SIFT features again are extracted from the current video frame and matched to the features already computed for the world mode, resulting in a set of 2D to 3D correspondences. These correspondences are then used to compute the current camera pose for the virtual projection and final rendering. A regularization technique is used to reduce the jitter in the virtual projection. 3D extensions of SIFT have also been evaluated for true 3D object recognition and retrieval. 3D SIFT-like descriptors for human action recognition, extensions of the SIFT descriptor to 2+1-dimensional spatio-temporal data in context of human action recognition in video sequences have been studied. The computation of local position-dependent histograms in the 2D SIFT algorithm are extended from 2 to 3 dimensions to describe SIFT features in a spatio-temporal domain. For application to human action recognition in a video sequence, sampling of the training videos is carried out either at spatio-temporal interest points or at randomly determined locations, times and scales. The spatio-temporal regions around these interest points are then described using the 3D SIFT descriptor. These descriptors are then clustered to form a spatio-temporal bag of words model. 3D SIFT descriptors extracted from the test videos are then matched against these words for human action classification. The authors report much better results with their 3D SIFT descriptor approach than with other approaches like simple 2D SIFT descriptors and gradient magnitude. Analyzing the human brain in 3D magnetic resonance images, a feature-based morphometry technique uses extrema in a difference of Gaussian scale space to analyze and classify 3D magnetic resonance images of the human brain. FBM models the image probabilistically as a collage of independent features, conditional on image geometry and group labels, for example healthy subjects and subjects with Alzheimer's disease. Features are first extracted in individual images from a 4D difference of Gaussian scale space, then modeled in terms of their appearance, geometry and group co-occurrence statistics across a set of images. FBM was validated in the analysis of AD using a set of 200 volumetric MRIs of the human brain, automatically identifying established indicators of AD in the brain and classifying mild AD in new images with a rate of 80%. See also, Autostitch, scale space implementation, references. External links, Scale-invariant feature transform and Scalepedia, Rob Hess's implementation of SIFT Access November 21, 2012, The Invariant Relations of 3D to 2D Projection of Point Sets, Journal of Pattern Recognition Research, JPRR, Volume 3, No. 1, 2008. Lowe, D.G., a OE distinctive image features from Scale-invariant K-points a International Journal of Computer Vision, 60, 2, pages 91 to 110, 2004. Michalakuk, K., and Schmidt, C., A Performance Evaluation of Local Descriptors, IEEE Transactions on Pattern Analysis and Machine Intelligence, 10, 27, pages 1615, 1630, 2005. PCA SIFT, A More Distinctive Representation for Local Image Descriptors, Lazanik, S., Schmidt, C., and Ponce, J., Semi-Local Affine Parts for Object Recognition, BMVC, 2004. ASIFT, Large Viewpoint Matching with SIFT, with Source Code and Online Demonstration, VLFEAT, an open-source computer vision library in C, including an implementation of SIFT, LIP-VIREO, a toolkit for K-point feature extraction, including an implementation of SIFT, Parallel, SIFT in C, SIFT algorithm in C using MGCOV and also a modified parallel version of the algorithm. DOH and log plus affine, blob detector adapted from a SIFT toolbox, a simple step-by-step guide to SIFT, SIFT for multiple object detection, the anatomy of the SIFT method in image processing online, a detailed study of every step of the algorithm with an open-source implementation and a web demo to try different parameters, EZ-SIFT, an easy-to-use standalone SIFT implementation in C++. A self-contained open-source SIFT implementation which does not require other libraries. A 3D SIFT implementation, detection and matching in volumetric images.